Welcome to Chapter 9 of the C++ programming language by Bajan Strutrop. Chapter 9 is on statements. So we're moving on from the different types from our Venn diagram. We're kind of taking a break from that, and we're starting to look at something that's also quite fundamental, which is statements. So beginning with 9.1, the introduction. C++ offers a sort of conventional set of statements. So a finite set that you can always pull from, and nothing more and nothing less. We talk about expressions in chapter 10, but statements specifically have no value. Right? So a statement does not have a value that you can sort of associate with that statement, unlike expressions. But the point of statements is to specify, so statements specify the order of execution. Right. So when we read code, we normally read it from top to bottom. And the idea is a block of statements, sort of one after the other, indicates the order in which those statements should be executed, or the order in which the instructions should be executed. So usually from top to bottom. So, for example, if I have something like this, a equals b plus c for some variables a, b, and c. Here I'll say int. And then I do something like if a is equal to 7, then reassign b to be 9. So in this case, we have 3 statements. This first one is probably always going to happen, right? That's an expression. We call that an expression statement because it's got an expression in it, and then it becomes a statement with this entire line. Then we call this an if statement, which is a conditional. That is, if a, the value a, is equal to 7, and if and only if a equals to 7 will we move into this sort of inner block here and run this assignment statement, b equals 9. Right? So, but we can see how the order of execution is sort of represented in the order that we write our statements in. All right. Now, something that was just sort of generally stated in the book is a declaration. Declaration is a type of statement. Right? So just when we think of declaring, we think about introducing a new name. That is considered a statement. And an expression becomes a statement when you add the semicolon. So again, if we look at that a plus or b plus c example, b plus c, that in itself is an expression. B and c will have values, and those values can be utilized in this way to come up with a new value, right? The value of b plus c. But when we have, especially that semicolon at the end, indicating the end of a statement, that expression becomes part of a statement. So that's how the chapter introduces itself. Just talking basically about primarily this idea of order of execution and the fact that the statements don't have values. Will be the main 2 parts. Now 9.2 is like a summary of all the statements that we're going to look at in the rest of the chapter. So I don't bother talking about 9.2. So we move on to 9.3. So 9.3 looks at declarations as statements. There's not much in here that's particularly new. It's more about some good practices to do with declaring. So unless a variable is declared static, its initializer, is the light? Okay, I'll skip. Unless the variable is declared static, its initializer is executed whenever the thread of control passes through the declaration. So just to clarify a few things, imagine I have something like int a, right? When we talk about thread of control, we can imagine that as you're reading through the statements, as the CPU is reading through the instructions, when the CPU starts to read, wherever the CPU starts to read, that is considered the thread of control, kind of like the flow of execution. And its initializer. So when we pass through a particular declaration, we can imagine that a is going to be initialized to something. Sometimes we will give it a particular value, right? We might say something like 3, for example, in which case the initialization will be 3. Sometimes we get garbage values if we don't provide a particular value. Sometimes we get garbage values, sometimes we get default values if we do default initialization. But there will be some kind of initialization that happens to the value when we declare it. Notice the only exception to that is if the object is static. Remember that static refers to the type of lifetime the object has. Is it recording? Yeah, okay. Type of lifetime the object has, and specifically, static means that the object is alive from the beginning of the program and dies only at the end of the program. So that's the only reason why static would sort of break this rule, because for static variables, they exist and are initialized from the very beginning. But yeah, for the most part, we can think of declarations as a type of statement that have to be executed, just like any other statement. We can just about declare variables anywhere before their first read usage. The first usage, but I guess more specifically, the first read usage. So what I mean by that, imagine we have this int a is 3, and this is my declaration and my definition, right? Oh no. We can declare variables. We can declare variables anywhere before their first read usage. All right. Yeah. So we can imagine this is my declaration. We can imagine that so long as this declaration is somewhere before the first usage, for example, we might declare int b and make it equal to a plus 4 or something. This is perfectly fine. In fact, a could have been declared anywhere before its first usage. It's only problematic if we try to declare a after its first usage, because again, statements are meant to specify order of execution. So since declarations are statements, they fall under that rule. So this should execute before this, but the definition of a isn't known until here. So that's the only problem with having declarations after their usage. But otherwise, so long as you follow that rule, you can declare variables wherever you want. Now, what's good practice? Good practice is to declare and define, generally, but especially declare variables right before their first usage. So in that, a becomes 3, b becomes a plus 4, int. Unless there's some extra reason why you shouldn't, there's no, it's perfectly fine. It makes a lot of sense to have a right before the b line, because you might as well. There's no point putting it really high up because you only start to use it here, and of course you can't put it beneath. Now for user-defined types, providing a definition with the declaration can actually improve performance. So for user-defined types, defining with the declaration can lead to better performance. So typical example would be something like a get a string. So using the string class in the standard library. So if I have something like a function void f, so function f, which first takes a string and declares it, string s1, and just declares it, no problem, and then says s1 is equal to hello. The reason why it specifies talking about user-defined types in particular is because user-defined types usually have something called a default constructor, or some kind of constructor where if no value is given, if no value is specified in the declaration, a default or some kind of value will be provided. So in this case, with no specified initialization value, the empty string is given. So whatever memory is required is allocated, and then in this case 1 byte, right? Because the empty string is 1 byte big because of that null terminator. 1 byte worth of data is associated with the string. So we first assign that to s1, and then give this hello string to s1, right? Compare that with if I immediately gave string s1 the value hello, right? what's the difference there? There is no empty string initialization, right? There is no extra sort of operation of giving the empty string and then giving the hello. It's just straight away giving the hello string to S1. So in that sense, we have improved performance. So especially for user-defined types where you've got default constructors, you would expect that giving the value straight away is better performance than sort of using the default constructor first and then giving like the extra string, the new string. Now, so in general, we expect that it's always good to define your variables as you declare them. So giving them some kind of value to work with. The only sort of, not the only, but the biggest case or the most obvious case where you might not want to do that is if you're using standard input. So sometimes a statement is required to obtain the initial value of a variable. I hope I skipped the line. Damn it, I smacked right into it. Sometimes a statement is required to obtain the initial value. Happens every time, and then a week passes, and then I forget. So yeah, so especially a very typical example of this is standard input. So you made your variable, you declared it, but you don't really have any appropriate value to give it because you're going to get that value from standard input. So as an example, let's see if I can if it's any better. Looks like it might be. So void f again, so it's function f. So we start by declaring some kind of buffer, right? So some kind of array that's going to store data in there. And max just pretend it's some global variable that I've declared beforehand. Just to allocate a certain amount of memory to the buffer array. And then we're going to have a count variable, equals 0. So initialize like this. And then we talk about for loops more, but this is a very typical way of getting standard inputs. You have something like std.cin redirected into I. So essentially what this is saying is while the user provides some standard input and that standard input can be redirected into I, you can do something like buff count plus plus equals I. Or maybe for now I'll just say count plus count equals I, and then we increment count by 1. Have we shown that already? Count plus plus. For now, I'm not sure if I've shown that before, but count plus plus is what that says, is basically just incrementing count by a value of 1. And here what we're doing is we're capturing we're assigning, the value of I, which would have been provided from standard input. Obviously, it would have been a character, but there'd be a corresponding ASCII number value that would be given to I, and we're going to plug that I value into this spot in the array. Right? So buff is an integer array, and the idea is we couldn't give it an initial value because there's no real reason to give it an initial value. Right? Even if we zeroed the array, especially if max is quite big, zeroing the array could be quite costly because we're giving a bunch of zeros to all these spots, to all these array spots that we're then going to replace very quickly with this standard input. So rather than giving it any kind of initial value, we just left it as a declaration, and then we have used standard input to at each spot from count equals 0 up to count equals whatever to put the I value in the array. So that's the only real, I shouldn't say that's the only. That's like a very typical reason why you might not give a value, something like standard input. Or I guess, like large arrays like buff, where zeroing the array is like not very performative. Isn't good performance. All right, so that's 9.3, talking about declarations. Now we talk about selection statements. So this is a particular group or branch of statements. Selection statements. So let's say you want to test a value or values. What do I mean by test? Typically we mean comparing two values together, checking if one is bigger than the other or smaller, things like that. So comparing or checking, testing a value. We can do this using if or switch statements. If or switch. So if we talk about if statements, usually they look something like this. If and then you give it some condition, and we'll talk about conditions, I think, in a bit more detail. Then do some statement. So that in itself could be an if statement. We can also extend them by having an else clause. That is, if this condition is true, do this statement. Else, if the condition is false, do this statement. Right? So it kind of makes sure that if one branch doesn't get hit, then we do the other branch instead. So you can kind of graphically, you can think of like, that's the if-else branch, if-else statement. And we have these kind of two branches in execution. If the condition is true, we go this way. If the condition is false, we go this way. You can have multiple branches. If you go if some condition, then do some statement. Statement, and then else if condition, some other condition, condition 2, then do some other statement, and so on. We can have as many else ifs as we want. Else if some condition n, so to speak, we do some other statement. And if you want, again, you can have an else as well, with no condition, just as a fallback statement. So note that every if, so we're talking about if or switch statements. So note that every if statement, every one of these kind of blocks, definitely needs an if. Okay? But if you want, you can omit everything else. It can just be an if statement like this. It can be an if and else like this. It can be if, else, if, and else, right? So if and then a bunch of else's and then an else. Or you don't even need the else here. You can have if and then some else ifs, but then no else. So the only compulsory thing to have is the if statement, the original if statement, for an if statement to work. And then for switch statements, I might write it over here. You usually have something like this: switch, and then some condition, and then you'll have the brackets, and then you'll have cases. Case. I shouldn't use actual things. You'll have case X, and then statement, case Y, and then some statement, and so on. You can have a default case, which is kind of like the else in this example. It's kind of like the fallback. If none of the conditions work, then we definitely run the else branch. Same here. If these cases don't work, or these cases don't catch your condition, then you run default, but you don't need the default. The default is optional. Depends on if it's appropriate for your use case. So we'll talk about these in more detail, but hopefully that gives an idea of what these things are used for. This idea of being able to check a value, or check something in this condition, and if that condition is true or somehow matches a case, then we run the corresponding statements. Okay. So a condition. So yeah, we haven't really formally introduced conditions yet, but I guess the first thing to say is a condition. So whenever I write condition in that example, a condition can either be an expression, whether that's a Boolean expression or an arithmetic expression. So yeah, an expression is either explicitly or implicitly Boolean. And we look a lot at conversions, I think, in chapter 10. But yeah, something that's either implicitly or explicitly Boolean, or a condition can be a declaration, which is more interesting, to be fair. I feel like I work with the declaration conditions less. This is more typical, but this is far less typical. All right. So now we look at if statements in more detail. So we've seen kind of their structure, how we would generally sort of write them in terms of pseudocode, but what would they really look like? So 9.4.1 is if statements. So in an if statement, we find the topmost condition that evaluates to true, right? And execute the corresponding statement only. So only the statement that corresponds to that particular condition is executed. Everything else is not executed. So i.e., at most one statement is executed. So at most one statement, I should say statement block maybe, is executed. If no condition evaluates to true, and an else statement is provided, then run the else statement. Execute the statements under the else block. Otherwise, so that is, none of the conditions evaluate to true, and there is no else given, no else statement is given. If it's that case, then no statement is executed. No statement block is executed. Not sure if there's any particular example. I don't think I have examples written, but I will do a simple one. So imagine we want to test if a number is divisible by 5 or 3, right? It's a very typical thing. I want to keep my notes if I can. So, yeah, so let's say we have some integer n that's passed into a function, so like void f integer n. So this value n is going to be passed into this f function. We can say something like if n is divisible by, so the operator for that is the percentage sign, modulo. If it's divisible by 3, and we say equals to 0 because the modulo operator gives the remainder after you divide by a number, so n divided by 3, and then what's the remainder of that? So if it's 0, you know that n is divided by 3, divisible by 3, sorry. So if n is divisible by 3, then print divisible by 3, for example. And we can say else if n 5 is n mod 5 is equal to 0, then we can say print divisible by 5, and then pretend that it's continuing on. But else, we can say something like print not divisible by 3 nor 5. That is, the number n is not divisible by 3, and it's also not divisible by 5. So, just to like run through this code a couple times, imagine n equals to 6. What would happen? Well, you would run n divisible by 3. Like, you would check this condition first, right? The topmost. Check this one first. 6 would give a remainder of 0 when divided by 3, so this would evaluate to true, right? This is a true statement for n equals 6. So we would run this, and then everything else gets ignored, right? Because we run the topmost condition, that is true, and then we call it a day. Let's say n is equal to 10, then the first one would evaluate to false, right? N is not divisible by 3 here, so when n is 10, that's not going to work. So we go to the next one, n divisible by 5 gives a remainder of 0, right? 10 mod 5 does give 0. So that would run, and then nothing else would run, right? The topmost statement evaluates it true, and so we would run that line. What if n was 22? Then both of these statements would evaluate to false, right? Because n is not divisible by 3, and n is not divisible by 5, and so we do the else statement. Let's say it's not divisible by 3 or 5. And then what if n was divisible? What if n was 15? Right? What if n was 15? Well, even though both these statements are true, right? N is equal to 15. Remember that we only do the topmost condition that evaluates to true. So even though both of these would be true, this is the topmost condition. So we would run this one. Okay. What if we wanted to explicitly mark statements that are divisible by, what if we wanted to explicitly mark numbers that are divisible by 15, right? So we can propose like else if n 15 equals 0, that is, if we were to get the modulus or the remainder after dividing by 15, then we would get 0, that is, n is divisible by 15. Else, if this is the case, then print divisible by 15. Right? This is sort of one proposed solution you could try. The issue with this, though, is remember, if you're divisible by 15, then you're going to be divisible by both 3 and 5. So which condition will actually evaluate first, or what is the topmost condition that will evaluate first? Well, we have if, then else if, then else if. So even though we have this condition, it will never run because the n mod 3 condition will always evaluate the true. For example, you think of the number 30. It's divisible by 15, but because we always do the topmost condition, this guy would evaluate the true first, and we would print divisible by 3, and then else if would be completely ignored. So if you wanted to do the divisible by 15 check, you'd have to do it first. It would have to be the first thing you check, then check 3, then check 5, and then if you want, you can check an else. This is also a good example. If again, let's say n was 22, all of these would evaluate to false, right? False, sorry. If, as in all of these are not true, right? And 22 is not divisible by 3, 22 is not divisible by 5, 22 is not divisible by 15. So all of these would evaluate to false. And since we have no else statement, it would be as if nothing happened. There would be no execution, essentially, because after these checks are done, there's no else to catch any leftover cases, so nothing would happen. So those are kind of all the things to think about with if statements. Order of execution, which condition is going to be evaluated to true first, and that is the only that's the only statement. That's the only statement block that's going to actually run. Okay, if a condition. Oh yeah. So remember we said that a condition can be an expression, either an explicit Boolean expression or an implicit Boolean expression. That example with the equals, right, and mod 5 is equal to 0, is a Boolean expression because when you check equality, that quality can either be true or false. Either it is equal to 0 or it's not equal to 0. So that is an explicit Boolean expression because we are explicitly going to check if one thing is equal to another thing and check if that's true. We're going to check if it's true that one thing is equal to another thing or not. So that's an explicit thing. But what if I did something like if a plus b, and notice I'm not checking if it equals anything, I'm just asking if a equals b, and we say int a, maybe I'll pass them in as functions, pass it into the function, so void f int a int b, and then I'm checking if a plus b. So there's no Boolean kind of representation of that immediately. A plus b, like we're not checking if it equals anything, not checking if it's bigger than anything, smaller than anything. It's just if a plus b. So what happens is the non-Boolean expression, this is a integer expression, right? This is two integers adding together, it's going to become an integer. The non-Boolean expression will be cast or will be converted into a Boolean value implicitly, without you explicitly telling it to do that. So remember from the Boolean chapter in chapter 6, we say that int can be converted to bool, where 0 becomes false, and anything else becomes true. Okay? So we have this kind of mapping. So, for example, if a is 3 and b is 5, then a plus b will become 8, right? So it's not 0, it's anything else, so that will evaluate to true. That will evaluate to true implicitly, and so this inside the block here, the statement block here, will run whatever's in there. Maybe we can say like print inside if something. Inside the if statement. That's if a plus b is not equal to 0. However, let's say a is minus 3 and b is 3. When they add together, you're going to get 0, which will implicitly be converted to false, which means this if statement isn't going to run. This if block isn't going to run. So if you had an else, for example, then that would run, but otherwise it would basically just skip over this execution as if it was never there, right? Now, we can do something similar with pointers. In a similar way, we can say, so remember that for a pointer to be converted to a bool, it's a very similar thing. The null pointer gets evaluated or gets converted to false, and anything else, any other pointer gets evaluated to true. So yeah, let's just get rid of this. We can say int star p. We can say if p, then print the inside if. So very similar idea. If p is storing or pointing to an address that is not to the null pointer. So if p is not the null pointer, it's not pointing to it's not the null pointer, then that will evaluate to true, and so this will run. If it is the null pointer, if you do pass in p equals a null pointer for this function, then p will be this statement will implicitly be evaluated to false, and so this particular if block will not run, and it will jump over it. So that is that. Cool. Okay, so something else to think about is plain enums versus enum classes. So this is us linking up with the last chapter stuff. So imagine, I think maybe first I should record. There's the light. Okay, so like there's fine. Remember that enum classes have strict type. So implicit conversions to booleans will not work. However, with plain enums, such conversions are allowed. So I think I have an example. Yeah, so imagine you have a function f which takes in two variables, e1x, so e1 is the type, and e2y, right? And so just to clarify, e1 is a plain enum, I think. Yeah. This is a plain enum that we've defined somewhere else, and e2 is an enum class. So plain enum versus the enum class. So imagine within my function, I do something like if x, and then run. Right? This is fine, because whatever the value of x is, remember that enum types, both enums and enum classes, are basically represented as some integral value. Each of the enumerators are represented by some integral, whether it's an integer, whether it's an int, whether it's a char, whatever, some integral type under the hood. So for plain enums, when you try something like this, where x is of type E1, that will be implicitly converted firstly into its integer type, and then from there will be converted into the Boolean, right? If it's 0, then it will be false. If it's non-zero, it will be true. So that is completely fine. These implicit conversions are fine for the plain enum type. However, what if I tried it with the enum class? If y, then we would have problems, right? Because the implicit conversion firstly into its integer and then into its Boolean, into the Boolean world is a problem because of the strict nature of the typing system for enum classes. If you really wanted to work with if statements and enum classes, you'd have to be very careful, I suppose, to actually compare y to something to the actual value. So like if y equals e2 ... red, for example, taking the examples from last time, the color examples, this would be okay because you are explicitly using a Boolean operator, right? You're comparing two things, checking if it's true that these two things are equal. So that would work okay. And remember that we have to use the scope resolution operator because scope is also quite strict for enum classes. But this is okay. But to just try and implicitly convert an enum class into a Boolean is a problem. But it's okay for plain enums. Yeah. Okay. We do get to look at operators a little bit, which is good. So we can start with some arithmetic comparison operators. I don't think there's much to actually talk about, rather than just make sure everyone is aware of what they look like. So arithmetic comparison operators. So these are the operators you would use to compare two values that generally have some kind of numeric value associated with them. So for example, the ones that I guess I had in my mind were the equality operator. I feel like I've written this a bunch, but I've never really talked about it. One equal sign is for assignment, right? It's to give a value to someone or to a variable. Two equal signs is comparison. It's an equality comparison, checking if the two things on either side have the same value, right? So equal, equal. Exclamation mark equal is not equal, right? So exclamation mark you'll see basically usually stands for not in programming. So whereas this is checking if two things are equal to each other, this guy's checking if two things are not equal to each other, and will essentially return true or evaluate to true if the two things are not equal to each other. So if you put a 1 here and a 2 here, that overall expression, would evaluate to true because they're not equal to each other. It's true that they're not equal to each other. However, if you put 1 here and 2 here, this guy would evaluate to false because 1 and 2 are not equal to each other, so it's not true, or it's false to say that 1 is equal to 2. Again, and then similarly we have less than, right? If you put a 1 here and a 2 here, that would evaluate to true. You can say less than or equal to. 1 here, 2 here would evaluate to true. 1 here and then 1 here would also evaluate to true, right? Because less than or equal to, it's the less than symbol followed by the equal to symbol. Then greater than 1 here, 2 here would evaluate to false because 1 is not bigger than true. 1 is not bigger than 2, sorry. And then greater than or equal to, same thing. 1 here, 2 here would evaluate to false because 1 is not bigger than or equal to false. But if I put 1 here and 1 here, this would evaluate to true. Whereas 1 here would evaluate to false because. Okay, so those are the arithmetic operators that we can work with typically, and that's what they look like. There are also the logical operators, and these are more this sort of slight extension, I guess. So there's three that we look at. There's the AND operator, or the conjunction operator, which is two ampersands, not to be confused with R-value references, right? R-value references you usually expect to see when you're declaring stuff, but in if statements and stuff, where you've got conditions, you would expect that's where you would see this kind of double ampersand. The double pipe symbol, right? So it's like, I know on my keyboard, it's like if you do shift \, you'll get that. So two of those is the disjunction or the OR operator, and then the not operator. Like I said, exclamation mark usually stands for not, and that's what it's used in this case. So this is the AND, or the conjunction. This is the OR, or the disjunction. And this is the not, or the negation. Right? So here we got three logical operators. So what's the point? What is their purpose? Well, primarily, it's to combine simple Boolean conditions into more compound or complex Boolean conditions. So for example, let's say I want to check if x is between 2 and 5, right? Unfortunately, as far as I'm aware, you cannot do something like this. If 2 less than or equal to x less than or equal to 5. I don't think this works. Okay? It would be nice if it did, but I don't think it works in C++. What you would generally have to do here is something like this. If x is greater than or equal to 2, we'll say inclusive, so 2 and 5 also work. If and x is less than or equal to 5, then do this. Okay, so understand that for conjunction, for the and, the double ampersand operator like this, in order for this entire thing to evaluate to true, all the individual bits, all the individual conditions have to evaluate to true, right? So x has to be greater than or equal to 2, and x has to be less than or equal to 5. If either one of these is false, let's say x is equal to 6, in which case that's true, but that's false. If that's the case, then the entire thing evaluates to false, and this if block will be jumped over, right? Same thing if x was like 1, for example. That might be true, but that would be false, and that's a problem, right? Looking at the OR operator, let's say I want to check if x is less than 2 or greater than 5, right? So like before, if I have an underline, yeah, that's fine. Before I was checking if x was somewhere here, right? Now I'm checking if x is either here or here. Okay, so one way, using the OR operator, one way we can do this, right, is saying if x is less than 2, strictly less than 2 this time, strictly less than 2, or x is greater than 5, then blah, 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 then do this, right? So what's this saying? Before we had an and, we said this entire thing evaluates true if all the little bits evaluate to true. This time, the OR means only one of them has to evaluate to true, in which case the entire thing is true. And when I say one, I mean at least one. So if that one's true, or if that one's true, or if both are true. In this case, it's not possible for it to be true, but if both were true, that's fine as well. But so long as at least one of these little conditions is true, then the entire thing is true. So if x is equal to 0, we would say this is true, right? 0 is less than 2, yes. This is false, 0 is not bigger than 5. But since at least one of them is true, then the entire thing evaluates to true. If x is 6, then this would evaluate to false, which is a shame, but that would evaluate to true, so then the entire thing would evaluate to true. If x was 3, then we have problems, because this would evaluate to false, and also this would evaluate to false. And so the overall thing would evaluate to false. So with and, if everything was true, then the thing is true. That's the only way to make and the and thing true, to make conjunction true. Or everything has to be true, then the overall condition is true. But for disjunction, for the OR, if everything is false, then the overall expression is false. That's the only way to make it false. If every little bit is false, then the entire thing is false. Otherwise, if even one of the things is true, then the entire thing is true. That's disjunction. Now, talking about the not I think of it basically as like a Boolean expression flipping thing. It switches the evaluation. So we can take the same example as before, where, as this one, we take the same example. So we're trying to still get less than 2 or greater than 5. But imagine I do it this way. If x is greater than or equal to 2, and x is less than or equal to 5, right? Still the same example. I want to be out here. So you look at this and think, well, what are we doing? Because surely that's the problem. We've got the exact opposite of what we want. But that's where the not comes in. Notice how this guy basically gets, basically corresponds to these values in between 2 and 5, right? Inclusive. So it's exactly the opposite of what we want. And when we get the exact opposite of what we want, we can apply the not operator or the negation operator up front, right? Usually, yeah, we wrap the thing we want to negate, we wrap it in brackets, in parentheses, and then put the exclamation mark up the front. By doing that, we flip the evaluation. So if this was originally looking for guys here, for x values in here, the negation looks for everything outside of that range, right? So as a very, if we work through an example really slowly, if we say x is equal to 3, originally that guy in here will evaluate to true, right? X is greater than or equal to 2, and x is less than or equal to 5 if x is 3. That evaluates to true, which means with the exclamation mark up the front, that flips the evaluation. So if it was originally true, it now becomes false, which is what we wanted, because we don't want anything in here. Anything in here we negate and cause it to turn false. And anything outside would originally be false, right? If x is 1, for example, if x is 1, for example, then this would evaluate to false. So this entire thing would evaluate to false. But then with the exclamation mark, it would flip it and evaluate to true, which is exactly what we want, right? We want it to be true if we're outside the 2 and 5 range. So the not operator basically is the negation operator. Flips the evaluation of a Boolean expression. Now there is this sort of, it's not strictly in this chapter, I think it actually comes up later, but there's this idea of short circuiting, just really quickly, specifically for disjunction and conjunction. So imagine you have condition 1 and condition 2. And then you have condition 1 or condition 2. Right? Remember what we said about the ampersands, the and, the conjunction. If one of the things is false, then you're in trouble. Everything has to be true in order for this thing to be true. Each individual condition has to be true in order for the entire thing to be true. So as soon as you figure out one is false, then you know that the entire thing is false. You don't have to keep looking at the other conditions. You don't have to keep checking the other conditions. So this is where this idea of short circuiting comes in. If you can prematurely determine what the evaluation is going to be, there is no need to continue checking conditions. So for example, if you check condition 1 here and you find out it's false, there is no point in checking condition 2, because even if condition 2 is true, this entire thing will evaluate to false because of condition 1. So what will happen is, after condition 1 is evaluated, if it is found to be false, then it will not bother. The execution won't bother with condition 2. It will just move on, right? Because it knows to evaluate this entire thing to false. In a similar thing, if we have the disjunction, and we happen to check condition 1, and it happens to be true, right? Because condition 1 is true, we know that the disjunction, regardless of what condition 2 is, we know that the disjunction will evaluate to true, because at least one of the things is true. And so, we won't bother checking condition 2, the execution will just move on. It will immediately evaluate this entire thing to true, and it will work with that as it will. So that's the idea of short circuiting. I believe standard says that you always go from left to right when doing short circuiting, but I'm not I'm pretty sure that's correct. So what the implications of that is, from a practical perspective, is you generally want to check your cheaper conditions first, and your more expensive conditions later. So for example, checking if one number is smaller than another number is not very expensive, so a quick thing, you look at two numbers. But maybe a second condition might have to do a series of checks to check if something is true or false, and so that's more expensive. I don't have any contrived examples this time, but generally speaking, you put your cheaper conditions on the left, because if you can sort of if you happen to evaluate either false over here or true over here, you can short circuit and you don't have to bother with the more expensive conditions. All right. Switch statements. Okay. Switch statements are pretty fun. They're a little bit unpredictable, so to speak. You haven't worked with them before, and it's easy to sort of mess them up a little bit. Let's put these back. We have time. Okay, not too bad, not amazing, but not too bad. 1, 2. So 9.4.2. Switch statements. So with if statements, we saw that you could do if, else if, else if, else if, and then else if you wanted. Right? This idea of checking one condition and checking the next condition, checking the next. And if as soon as one of those things evaluates the true, we run that particular block, and then everything else gets ignored. Switch statements are a little bit different. Generally, the overall goal is to select among a set of values, case labels. So whereas before with the if statements we had like, equals to, not equal to, greater than, less than, like that. Generally speaking, I think of switch statements as only really having an equal sign operator that you can work with. So the expressions in case labels, case labels, they would say labels, must be a constant expression. Now, we get a more formal definition of what a constant expression is later on in chapter 10, I believe. Yeah, it must be. Chapter 10. But for now, think of constant expression as basically something where you know its value before you run any code. So like literals or, we'll say literals. So there's a couple of others, but literals are the easiest one to think about. So like the number 3, you don't need to do any sort of runtime code execution in order to know that the value of 3 is 3. Like, we know that value, so that's a valid case label. So think of constant expressions, I should say, of, there's a couple of extra specifications, integral or enumeration type. Let's add this part. So for now, think of literal integrals, right? So literal integers, char types, literals of those, or enumeration types. So if you define any number beforehand, you can use those enumerators, right? The red, yellow, green, whatever. You can use those as case labels. So a couple other rules is you can't use floating point values, so floats and doubles are out, and you cannot have duplicate labels. Now, it's very easy for me to write all this, but what am I actually saying? What is a case label? What is how would I actually use them? So we'll write a quick example. Imagine you have a function. No, my pens are here. Sorry. Imagine you have a function, as always, that takes in an integer v. Okay. So imagine we're going to check if v has a value of 1, then we want to do something. If v has a value of 2, we want to do something. If v has a value of 3, we want to do something, and otherwise just say v is not 1, 2, or 3, whatever, right? Okay. So what would we do? We would do something like switch v. We introduce the switch statement, switch, and then we, in brackets, put the thing that we want to be checking the value of, in this case, v, right? It's an integer type, so that's fine in this case. Integral or enumeration type, it's an integer type, that's fine. From there, we do something like this. Case 1, colon. Case 2, colon. I actually don't think it's typical to put indentation. You actually put it right underneath, I think. Case 1, case 2, case 3, it's also default. Okay, so what would happen? Well, v would be compared to a particular case, and whichever one matches, it would begin execution there. So if v is 2, for example, it wouldn't bother with 1, because it doesn't match, and then it would go to 2. Right? Now the difference is with if statements, once a condition is met, right? Once a condition is met, set to true, it is found to be true, only that one particular block, that one particular statement block is run, and everything else is ignored. Here, without any other specification, if you just matched v to be 2, the code under the case 2 would run, but then the code under the case 3 would run, and the code under the default would run, which oftentimes isn't intentional. We don't want this cascading effect, we say, where case 2 runs, but then case 3 runs, and the default runs, right? So this is the general structure we want, but how do we make sure that only one case label worth of execution, or one case label's worth of statement actually runs, right? But this is a general structure, so that's a good way to start. Note that we could use an if-else statement instead. If we wanted, we could say, if v equals 1, then do this. Else if v equals 2, then do this. Else if v equals 3, then do this. Else, so the else is kind of like default. Else, do something else. And note that the default isn't necessarily required, right? It's available, but not a necessity. Kind of like the else. So yeah, talking about this cascading thing. So there's actually a better example that I should have used, but it's fine. I should have started my example here, I think. But, okay, so yeah, let me just basically write this better. Switch val, we have our brackets. So I'm basically taking this switch and I'm doing a bit more. And then I have my case, so not val, be case 1. And then let's just say I print case 1, basically. And then case 2, and I print case 2, and then, okay, I didn't bother with case 3, let's go straight to default. We can print default case. Okay, so just to reiterate, what happens when you run this code straight away as it's written? Let's say v is equal to 3, we'll start 3. It won't match case 1, it won't match case 2, it will go straight to default, print this, we're done, as expected. However, if v is 1, it will match with case 1, print this, but instead of moving on from the switch statement, jumping over it, it will do case 2 and do default as well. Because there is no, I guess, to explain why it does that, in essence, the scope or the block of a switch statement is here to here, right? Each individual case, unless you specify Each individual case doesn't exactly have its own scope or its own sort of individual block, the way that if-else statements have their own individual squiggly brackets. The squiggles are here and here only, right? So once you're sort of in here, the code or the execution flow still has access to these labels underneath, right? If v equals 2, you jump over case 1, in which case you won't be able to go back to it, but after you get to 2, it will print case 2 and then flow down to default and print the default as well, right? So what do we do to avoid this cascading effect? We add the break keyword. Oh, I didn't actually write that explicitly. That's good. Okay, anyway, I'll just write it here. Wait, okay. So, and underneath our execution statement, we break, and I think we talked more about break in the for loop section. But what you want to think of breaking, when you see the term break, you're basically breaking out of the innermost scope. So in this case, the innermost scope is not the cases, it's the switch. So when you see this, so if v equals 1, you print v1, and you see the break, you break out of the scope, and therefore you jump to here, sorry. You jump out of the scope, so you skip case through case and the default, and you go to here. That's what the break does. Notice I didn't bother putting a break here, because breaking here is the same thing as just continuing on from default. There's no real need to have a break. But here and here, you need it, because without it, you would continue in that downward fashion. Breaking lets you jump over any cases that you want to skip after you hit a particular case. Sometimes, I'm not actually sure when, but sometimes you might want the cascading effect if you find that that's what you want. But it's a good idea to add a comment saying, hey, I actually meant to leave out the break in this situation. I actually want the cascade, because if a programmer looks at your switch case statement and sees that you're missing a break or missing some breaks, it's easy to make the assumption that you forgot the break. A lot of people will think that you forgot the break rather than thinking that's intentional. So it's good to add a comment saying, hey, I actually want no breaks here because I want the cascade effect. Like what? Oh, I skipped a page. That's right. Yeah. So talking about default, generally we expect default to be used if we have an error to check for error cases. So let's say the only valid values for v are 1 and 2. That is, this switch statement should only take in a 1 or a 2, right? In which case this is perfect. And then if you hit the default case, you know that the v value is incorrect or somehow invalid. So you could print something like, oh, error, v should be 1 or 2, right? The default can be used for error checking. You can also use it for the most common value or the most common case, like what is the most common case for the v value to be. But I've personally found that a little bit or less comfortable. I found that a bit comfortable. But that's in the book. You can use it for the most common case. However, the big one where you shouldn't use default is when you're going through enumeration cases. So what do I mean by that? Imagine you have an enum class. And the example is kind of weird, but you call it vessel, and your enumerators are cup, glass, goblet, and chalice. Right? So remember each of the, I forgot, enum class vessel, cup, glass, goblet, and chalice. Right? So remember each of these is an enumerator, right, with a particular, so a type, a variable of type vessel can take on one of these values, right? Imagine we have a function void f which takes in a vessel v. And imagine we want to, based on what the actual value of v is, we want to run some certain code. So we switch on v, checking its value and comparing it to our labels, and we say case vessel cup, colon, and then do whatever, and then including the break probably. Case, vessel, glass, colon, and then do whatever. Case, vessel, goblet, colon, and then do whatever. Now, because we have 4 cases, right, it might be tempting to think that, well, I've exhausted the other 3 cases, in the first 3 cases of my switch case, so I can just write default. Right, to handle the last chalice case. However, it is, by doing this, you essentially suppress the warning that the chalice case is missing. Essentially, if you were to not put the default in there, then the compiler would recognize that you haven't actually checked for the chalice case, and so it's possible that you can get a warning, and that might be something that's good, because then you're like, oh, I forgot the chalice, and then you get it in. Having default here can be problematic, because it will suppress that warning, because it says, oh, well, the chalice case will be caught in the default, so that's fine. Which might seem okay, like, I mean, that's what you wanted, to catch the chalice case in the default, but if there is some kind of corruption with the v value, for example, v stores a weird integer value that doesn't actually match with one of your numerators, the default will handle that case as well as if it was chalice. In that sense, that's a problem. So you want to be very explicit with your comparisons, and in this case, say that case, vessel, chalice, colon, and then do whatever you want. So be super explicit about all your cases with enumerators and enum classes. Okay, so there's one extra rule that's actually tripped me up a couple times when I've just been like practicing stuff when it comes to switch cases, and that is regarding declarations within your cases. So we can declare variables within the block of a switch statement. However, it is not possible to bypass or jump over initialization. So I'll try to add code, I think, on screen, because I'm not sure if I even fully remember this. But imagine you have something like this: switch, and then some x value, and then you have your opening case 1, and then we say int y equals 3, and then we break out, and then case 2, blah blah blah, whatever it is, break, and then default blah blah blah. Okay, so if you were to write this code, there would actually be some major problems, because remember how scope works inside the bracket. Remember what scope works with switch case statements. Even though it looks like case 1, case 2 are kind of separate, especially since we have a break, in terms of scope, they share the same scope. All of this is within the one switch scope. So when the compiler reads this, it has a problem, because it recognizes that int y equals 3. Y is originally initialized at case 1. But because it's within a particular case, it is possible for this initialization to be jumped over if, for example, x equals 2. If x equals 2, this initialization is bypassed, right? It's jumped over, and we go sort of to here straight away. We have jumped over an initialization, which the compiler is worried about, because it's possible, because of that scope rule, it is possible that case 2, for example, might use y, right? It's possible, because they share the same scope. So in order to prevent those kind of errors, it basically says, I'm not going to let you jump over an initialization in the first place, right? Because it's possible that y might exist here or here, and if that happens, then we're going to have problems, because we never did the declaration or initialization here. Especially we didn't use the initialization here. So we cannot bypass or jump over an initialization. If we want to get around this, what we have to do is specify that the y is within its own block, is within its own scope, right? We add squiggly brackets. Remember that squiggly brackets indicates the beginning and ending of a block, right? So by adding these sort of this artificial block, we essentially encapsulate the int y equals 3 line within its own scope, which means y is not accessible outside of the case 1, right? And in that sense, it will be okay to jump over it, because the compiler is now happy, like, okay, there's no way that any other case is going to be using that y, because it's encapsulated within a scope, right? That squiggly bracket is after the break, by the way, not before, just to make sure that's, yeah. And this is after the case 1, but before the int y, so it's within there. So that's how you can declare and define and initialize stuff within a particular case without the compiler being concerned about it being used in other cases. Okay. Yes. Okay. 9.4.3 looks at declaration conditions. So we said that a condition could be a Boolean expression, either implicitly or explicitly a Boolean expression, or it can be a declaration. So declarations in conditions. Let's get water. Alright. So a variable declaration in a condition must have an initializer. Okay? So what does it look like? What does it look like to have a declaration in your condition? Something simple might be if int a equals 3, then print a. What do you expect this to look like? What do you expect to happen? Well, if this works, then this should print 3. Right? What have we done in this situation? We have assigned the value of 3 equal. 1 equal, remember, is not an equality operator. It is the assignment operator. So we have assigned the value of 3 to the integer a, and then we're printing a. Now the question is, does this evaluate to true? It does, because the assignment operator, in essence, returns returns the value that was assigned to the variable. So in this case, int a equals 3. That line happens, the assignment happens, and when it comes to evaluating this condition, it just takes the value of the assignment, so 3 in this case, and then uses that value. So in this case, because 3 would evaluate to true, right, because it's non-zero, it evaluates to true, so this would evaluate to true all the time, in this case, and so this print statement would always happen all the time. So it might seem a bit trivial, like, because of how contrived this example is, but imagine if instead of 3 we had, like, some other variable here, that you might not actually know what that value is, and then you could assign it in that way. But I hope that I can find good examples. Just to clarify the other way, if int a equals 0, print a, right? So if this print statement were to happen, we would expect it to print 0, right? Because we assigned the value of 0 to a, but remember that when it comes to evaluating this condition, in the assignment case, it basically checks what value was assigned to a, or what is the value of a now. And since the value of a is 0, this entire thing will evaluate to false, because 0 is converted to false. And so actually, this entire thing will be jumped over, because this is not true, so it will jump over it. So when would we use a declaration as part of the condition? Essentially, it's good for if you want to capture the result, typically of a function call, in a variable. And then based on the result of the function, choose a particular course of action. Right? So a typical example, or the example that is in the book, works with malloc. So malloc is sort of closer to a little is more focusing on memory management, which maybe is a bit more complex with sometimes, but in essence, we, especially on the heap, sometimes we want access to memory that we kind of will handle and work with. So what malloc does is it lets us sort of gain ownership of a particular chunk of memory. It's especially relevant in C, not C++, but for our purposes, essentially it takes in a number of bytes, right? And assuming there's sufficient memory, it will choose a chunk of memory that is gives that number of bytes and will return the address of the first byte of that memory, right? So if successful, if we are able to sort of obtain that chunk of memory, it will return a pointer to the first allocated byte in memory, right? If successful. However, if it fails, right? Maybe you just are using so much memory for other stuff that there's just not sufficient memory available for this malloc call. If it fails, then it returns the null pointer. Right. So what is the implication of that? Imagine, for example, that where's my red? There it is. Imagine, for example, we are doing something like int main, so in our main function, right? And we say if int star p equals malloc and like, I don't know, 64, then do this. Okay, so let's really then do some stuff. So what is this saying? We are first going to call malloc, do our best to gain 64 bytes of memory. I think it's bytes, yeah, it should be bytes. 64 bytes of memory. We're then going to take whatever the return value is, whether it's successful and we get the actual pointer to actual memory, or it's a null pointer. We're going to assign that to this pointer p, and then we're going to evaluate, right? So we're basically leveraging this idea of success and fail to trying to figure out if we could use p validly. Because if it's successful, it will return a legitimate pointer. This will return true, right? Because the assignment is a non-null pointer. So this entire thing will evaluate to true, and we can go on our merry way, right? Because p is a legitimate address, or p stores a legitimate address, so we're happy. If it fails, and this returns the null pointer, then p will be given the null pointer, and this entire thing will become false, and we won't do anything really dangerous, because we'll jump over this block. Maybe we can say else, print an error saying, hey, malloc failed, and I don't know why, or something, right? Else print error. Right, like, by doing this, we essentially can leverage the value of malloc and also get our assignment done all in kind of one swoop. We don't have to kind of check malloc and then sort of write it inside here. So we don't have to like run malloc outside the if statement and then check p separately and then go on. The other thing is, the other option we could try something like this: int main. We can do int star p equals malloc 64, and then if p, then do stuff. Else, do stuff. Essentially, this is equivalent in terms of like overall functionality. The reason why you would prefer this one, is because the scope of p is more restricted. P is within the scope of the if statement, assuming that's what you want. That you're only going to use p, and you should only use p after you check that it's okay, that it's not null. The scope of p is restricted after it's been checked for being the null pointer. That's what's really good about this. Here, what the risk is, and it might not seem like a very big risk for a small program, but as you get bigger programs, it can become problematic because you've created p outside of the if statement. Remember that the if statement makes sure that p is a valid pointer and not the null pointer. Because you've created p outside of it, it's possible that you'll accidentally use p before the if statement, before you've actually checked the validity of p. And so you might accidentally use the null pointer if malloc fails and p is given the null pointer. So that's the only issue with this kind of thing. The idea that your scope is a little bit wider than maybe it has to be. Here, because you keep your scope within the if statement, you can be really confident that the pointer p is safe to use. It is not the null pointer. So that's what that is. That was a bit long-winded, but hopefully... this is about the scope. But yeah, hopefully that gives a nice idea of why, especially if the function you call returns something like an integer or a pointer, and it returns sort of false or 0 or null pointer when something bad happens. It's in that kind of situation where something like this is helpful. Okay, so that's everything on selection statements. So we talked about if statements, switch statements, things to do with declarations and conditions, and a little bit to do with scope as well. So now we look at iteration statements. How are we going? Okay. Yeah, not bad. Okay, so 9.5 is iteration statements. So the types of statements. So we saw if statements and switch statements for selection. So for iteration, we have while, do while, or do statements, and for statements. So the way these typically look is while will look like this. So while some condition, do some statement block, and then do while or do looks very similar, except it's do some statement while some condition. Right, so while, then this, and then do, then while. For loops, there's actually two kind of types of for loops you can work with. There's the classic C style, so for, and then you have like for initial statement, some kind of usually declaration and definition here, semicolon, and then some condition, and then some expression. Update expression. And then after that, you have a statement within the block. Right, so initialization statement, condition, update expression. And then the other type of for loop you can look at is the range for loop, which is like the for declaration, colon, in the expression. Typically a container, but expression. And then for each of those, do the statement. Okay, so that's like the overview of what we're going to be looking at for iteration. Okay, so the general idea in all cases, regardless of which one you're doing, is the loop body, which is the stuff kind of within, like basically the statement block. The loop body will run. Did I? Oh, I did. I forgot. This. I think the only thing missing is it should say for. For init statement, condition, update expression, do the statement, and then that's in blocks. That's in a block. Yeah. Oh, it's so bright. It's like here. Okay. So the loop body will. The loop body will run. So the loop body will run until the condition. Right. Notice that basically all of them have a condition. This one doesn't, but we'll talk about for range loops in a second. Or range for loops in a second. But until the condition returns false. Or the other option is the programmer, the coder, uses some kind of jump instruction, uses a jump instruction. Jump instructions can look like break, return, throw, and goto. The only one we really look at is break. I think goto is talked about later in the chapter from memory. But yeah, the main thing we'll look at is break. Yeah. Okay, so range for loops. Or range for statements. So that's looking at this one, the one with the colon. I believe, unless I'm mistaken, yeah, no, there's no way. Range for loops is a C++ thing. Unless I'm like, unless I missed something. I don't think it was in C. So this was like the first, one of the first C++ specific things that I learned reading the book, I think. I guess I was like, there was email classes, but yeah, it was one of the first things. So, 9.5.1, range for statements. So, in essence, the goal is to get access to each element of a sequence or range. So imagine there's a function which takes in a vector. I feel like I keep mentioning vectors in passing. For now, think of vectors as an array, as a list, or as a sequence. The big thing about vectors is that they are dynamically allocated, so you can kind of increase and decrease their size, which is not true for normal arrays. But in this case, just think of it as an array. And this sum function is meant to get the sum of all the elements inside this integer vector. So we start with an initial value of 0. We say, for int x colon v, and then s plus equals v, and then we return s. Right? So what are we saying? This one meant to be blue. So the way to read this is essentially for each element, integer element, in v, from left to right, or maybe more accurately, from lower address to higher address. So again, visually, we can model a vector like an array. So v might look like this, right? A couple of integer spots, 3, 6, 12, minus 2. So what's going to happen is, for int x, we're saying for each integer x that's existing within the v, so this entire thing is v, we're declaring x and saying let it take the value of each integer in v. So x is going to be 3 initially, and then we're going to add that, oh, I should say x, sorry. Yeah, I made a mistake in minus. X is going to be 3, and we're going to add that to our 0, our counter, right? We're going to add that to our counter, so s is going to increase to 3. So x was 3, and then we're going to increase to 3. Then x is going to move on to here. It's going to become 6 in this loop. It's going to be added to s, so we're going to get to 9. It was 3, now it's 9. Then x is going to move on to 12. It's going to add that, we're going to get 21. Then x is going to become minus 2. We add that to s, we get 19. Right? So x, in each iteration of this loop, is going to take on each value of the vector, right? And it's going to run and do the instructions as asked. So yeah, the red is basically saying how you can interpret this line. For each element in v, from left to right, let x take each value. So let it take the 3, and then run the loop. Let it do the 6, then run the loop, then do 12, run the loop, minus 2, run the loop. So that's the general idea. After the colon must be a sequence. So after the colon here, what is allowed to be on this side? We can see that vectors can be there. I believe simple arrays can be there. But in general, there must be a sequence. This guy here must be a sequence. Now, what is a sequence? What is the specific definition in C++ of a sequence? A sequence is an object where v.begin, v.end is defined, or begin v and end v is defined. So you have to try one of these two things. Okay. Some classes, right, some types have inbuilt begin and end member functions, right? They exist as part of the class or as part of the struct, and so you can call that directly. It will try. So the compiler will try that first. It will check that these methods or these member functions exist, or the compiler will try to call these on the object that you put on the right hand side of the colon. So what's begin and end do? Well, begin gets the address of the first byte of the first element in your sequence, and that's for both of these. End gets the byte right after the last byte of the last element. Hopefully this idea of getting the byte right after the last element is familiar. We talked about it a bit with arrays. But just to clarify, imagine I have some vector like this, or some array. Right, we've got 3, 4, 2, and minus 3. Remember that for integers, this is integers, for integers, each element takes up 4 bytes, and integer is 4 bytes. So, for example, I can split this first guy into four pieces. Begin should get the first byte of that first element. That's what begin should do. End should get the byte right after the last element, so this guy here. Okay? So that's the point. That's what begin and end are supposed to call. Now, if you provide a type on the right-hand side of the colon, so if I do something like for int x in C, let's say, but C doesn't make sense to call begin and end on C, right? Because, for example, I mean, C could be a primitive type, right? Let's say C is a char, right? Imagine you declared C up top here as A. The primitive type, or the fundamental type char, doesn't have a begin and end interpretation, right? Trying to call begin and end isn't going to work on C. So the compiler is going to have a problem with this line because the C is not considered to be a sequence because these functions or member functions don't work with C. Vector does have a way of interpreting the begin and end functions, and so is considered a valid sequence, yes, a sequence type. The interesting thing, I have like a full-on example. So like I said, with user-defined types, if you want to use a user-defined type in this context, you'd have to provide an implementation for begin and end. So what do I mean by that? Imagine I create a struct. Struct S, and its only member is an integer array of size 4. And I'll do it like this for now. Okay? Let's say in my main function, I create a struct of type S, my struct, and I fill in the holes 11, 12, 13, 14. And let's say for int x colon my struct. And I just ask to print the value v, and then return 0. With this alone, my struct is not a valid sequence because the begin function, right, and the end function do not recognize the struct S type. So they're not going to work. They're going to say, I don't know how to handle this thing. And the members, like dot begin and dot end, these refer to member functions found within the struct. These member functions don't exist yet in the struct. So that would be a problem, because my struct is not a valid sequence. Nor should it be, because when you say my struct, of course in this case there's only one member, which happens to be array, but imagine I had other elements. How is this guy meant to know what I want to iterate through, right? Or if I had multiple arrays, how does the for loop know which thing I want to iterate through? So this is where defining the begin and end member functions becomes important. So what we would do is, similar to how we can provide these kind of declarations for variables, we can do a very similar thing with functions. We can say int star begin, because begin is meant to return the address, right? So it's going to return a pointer. Begin. This is the wrong thing. And we would return x. Right? Remember that when dealing with arrays and pointers, arrays can be sort of implicitly converted into a pointer. So when we return x in this way, what we're actually doing is returning the first byte of the first, we're returning the address of the first byte of the first element. That's what's actually happening there when we say return x. We're not returning the entire chunk of the array. We're just returning that first byte of that first element, right? And then in a similar fashion, we can say int star end. Maybe I'll just get rid of this one. And we can say something like return x plus 4. Okay. Remember from before, again, this would be converted into a pointer, right? And in terms of pointer arithmetic, if I have 4 elements, 1, 2, 3, 4, where x is associated with that first byte of that first element, adding 4 adds 4 lots of integer number of bytes. So we don't add 4 bytes, we add 4 integer sizes. So 16 bytes, so to speak. But we do 4 jumps. We don't do 4 bytes, we do 4 jumps. So 1, 2, 3, and then 4 gets us right after, gets us right past the final element, and that's why we would do it like this. Of course, this is severely hard-coded to handle these magic numbers and stuff, but for the sake of simplicity, hopefully it's clear that if x refers to that first byte of that first element, then x plus 4 gets us right outside the array. So that would be valid begin and end member functions, which means the dot begin and dot end functions now exist, right? These guys are still not recognized as struct, but the dot begin and dot end now exists. So my struct is now a valid sequence type. The compiler is happy with that. It knows how to handle it. So now when it reads this, basically, it knows where the first address is, and it knows where the last address is. And so, because it also knows the size, right? Integer is 4 bytes. It knows how many elements are in between, and where those, or more specifically, where those elements are located in memory. And so it knows that X should take each of these values in memory, right? And so that will happen no problem. It will print 11, 12, 13, 14 without any problems, because we now define the begin and the end member functions. Yeah, that's a good point. Okay, so in the same discussion, talking about these range for loops, or range for statements, imagine you want to modify values in the vector. So you have something like for int x colon v, and you say x plus plus. The goal you have is, imagine if the array, if the vector, so v is a vector here, if the vector originally looked like this, 1, 2, 3, you want to increase each value by 1. So you want vector to now become 2, 3, 4. Unfortunately, in this case, that would not happen. What would actually happen is when x gets created, it's created in a different place in memory. If this is sort of, if this is my slab of memory, for example, this is my v, right, my vector. But when I create my x variable, it's actually in a different spot, right? It would be also given the 1 value, but that 1 is copied across. It's not the same 1 as here. It's a different address. So when we increase 1, it becomes 2. And then x will be given the value of 2, so it's the same. Maybe I won't make it 1, 2, 3. I'll make it 1, 4, 9. So sorry, just to go again. X would originally take the value of 1. Then it would get increased to 2. Then it would move on to the next element, which is 4, and get increased to 5. And then it would move on to 9 in the loop, and then get increased to 10. And then, assuming there's no other uses for x, the scope of the for loop is gone, and then that x is no longer accessible. You haven't actually changed the values in v. You've just sort of messed around with some other memory somewhere else. So as the code is written, the vector itself won't be modified. But if we do want to modify the vector, right, modify things in place, actually modify these elements, we can ask for a reference each time. And essentially, that reference will refer to the elements in the vector. So when you ask for x to increase, what will actually happen is the elements inside v are being asked to increase, right? Because the reference is referring to objects in memory. We're not actually increasing x, we're increasing the thing that x is referring to. So in each iteration of our loop, firstly, that will increase it to 2, then this will increase by 1 to 5, and then this will increase by 1 to 10. Right? In essence, we are asking x to refer to elements in v, and when we ask x to increase, we're actually asking for the elements in v to increase. So it's kind of an alias. The only thing I'm a bit unsure about when I was writing this up was considering that references aren't meant to change what they're referring to. So in that sense, is it that x is always referring to the vector as a whole? Is it x is referring to this, then gets destroyed, and then a new x is referring to the next guy and gets like that? I'm not too sure, but I know that this is how it I know visually this is what it should look like if you want to modify stuff in an array or in a vector in place. But yeah, I should check further as to why this works and why it doesn't break that rule of references aren't going to change what they refer to. Right, yeah. The element variable. It's fine. Another good point. So this is one reason to use references here, right? If you want to modify something in place, so modifying the sequence elements, right? That's one reason to use a reference. Another good reason is if the element size, that is not the size of the overall vector, but the size of each individual element is large, then use a reference. Okay? Why is that the case? Remember that if we don't use a reference, what's happening is the x gets copied into new memory, right? So instead of 4 byte integers, imagine if these elements are I don't know, really big. I don't know how big is reasonable, but imagine it's like, this is one element, this is another element, and whatever, right? So instead of copying a cute 4-byte integer, we're now, every time we want to get to the next element, we have to copy like that, right? A big element, we have to copy it, work with it, and then we have to copy the next element, work with it, and then we have to copy the next element. And these are really large copies to have to do. So that's another reason why you might use a reference, because a reference is always just going to be referring to memory. It's not actually going to be copying large things down. So that's the other reason why you might use a reference. So modifying sequence elements themselves, and also to avoid copying large objects. So now we get to 9.5.2, which is more of that C style of for loops. So for statements. So yeah, this is a more general for statement. So the for range stuff, the range for loop, is for when you're really trying to iterate through is more when you're trying to iterate through a sequence, right? Going from first element to the last element. It's generally the use case. So the for statement is allows for some other use cases. In essence, you most typically you introduce a loop variable, right? Typically you might see something like int I into j. Introduce a loop variable, a termination condition, and an update expression. So, very classic type of look of a for loop. For int I equals 0, I less than 10, plus I, and we're just going to print I. A couple of things to note in terms of sort of variables. The scope of I is within this for loop. Outside the for loop, either here or here, I is no longer accessible. It is purely accessible kind of within this statement and then within the body here. In terms of execution, to really understand what's happening, the first value of I is going to be 0, right? It's going to run through the loop. It's going to check. Maybe I should start. Let me say that again. The first value is going to be 0. It's going to check that the condition is true. If it is, it's going to run the loop, and then it's going to increment, and then it's going to do the update expression. Okay. So I is set to 0. Is the condition true? Yes, because I should say I. I don't know if that's obvious. 0, right? 0 is less than 10. That is true. So we are happy to run the loop. So we print I, which is 0. And then we run the update expression, which is plus I, which means increment I by 1. So I becomes 1. We repeat. I is now 1. Is it less than 10? Yes. So print and then increment. Is it less than 10? Yes. 2. Now increment. Now it's 3. Is it less than 10? Yes. Increment. 4. Yes. It's less than 10. So increment. Print it and then increment. So now it's 5. Is it less than 10? Yes. So print it and now increment. Is it less than 10? Yes. So print and increment. Same with 7. Same with 8. Same with 9. Then we increment to 10. And we ask ourselves, is 10 less than 10? Strictly, no. The answer is no. So we do not print, and we jump out of the for loop, and we end up sort of outside here, right? So I don't know how clear that was, but the idea is you have an initial value, you check if your condition is true, and it's assuming it's true, you run your loop, and then you increment, or then you update. And that's the kind of order, over and over again. And then you'll get, in this case, you'll print out 0 through 9. Notice in this case, of course I didn't print 10, but the loop ran 10 times to print 0 through 9, right? There's 10 numbers here. So if you want something to happen 10 times, this is the typical thing it will look like. If you want something to run n times, right, for some number n, you would typically expect it to look like this, right? The other option, I guess, is not equal to. That's equally valid, but I guess out of my own habit, I tend to do less than. Sometimes you might want to start at a higher value and bring it down. So if I bring this back to 10, I'll use blue again. If I bring this back to 10, maybe I starts at 20, and then I should stay greater than 10, and then minus I. So you're bringing I down to 10 instead of bringing it up to 10. So 20, 19, 18, 17, down to 11, it will all print, and then it gets to 10, but that's false now, because 10 is not greater than 10. So that's false. We don't bother with the loop. We don't bother with the increment or the update, sorry, and so we jump out of the for loop. right? So that's how that works. If you do not need a loop variable, sometimes you don't need it. Sometimes you have some other variable from outside the for loop, and you're just going to be working with that other variable, right? So for example, you might have some Boolean variable like bool b equals true. And while b is true, you want to run some particular for loop, and sometimes at some point b might be set to false, in which case the for loop will terminate. If that's the case, you don't actually need to introduce the loop variable if you don't want to. You can keep that part empty, kind of empty declaration condition, empty declaration statement, and then you can say b as your condition. And in this case, I guess there would be no increment as well. So I believe you can keep that empty as well. And you might say something like, if I am sleepy, then b equals false or something. This is I'm getting a bit tired. That's why that's the inspiration of that. But in essence, what's happening here is the only part of our for loop that exists now is the condition part, checking if the condition is right. There's no loop variable. There is no update because it's right. And you're doing stuff within your for loop, and maybe else you go for a run or something until you're tired. Maybe I say tired instead of sleeping. So basically looping over and over again, right? B is true, so it's going to just loop over and over again. I'm going to keep going for runs until I am tired is true, and then B will be set to false, in which case this condition will be false, and so it will jump out. So it's technically not necessary to have the loop variable or the loop update, like the update statement, if you have another way of terminating, maybe some other variable from before. But in this case, even this is kind of stupid, because you could very easily just say bool b equals true. And this will do the same thing. It will even be better because the scope is restricted to the for loop, right? Unless the only reason to have it outside is if you have some other reason for b to be used, right? But that's just an example. You don't necessarily need to have the initialization. Now the weirdest case is you have nothing. What that means is there's no condition to check is true. So in essence, this will always just continuously run forever. If you have there's no initialization, there's no condition to check especially, and there's no update, then this is basically just a run forever loop. Again, you can use break statements or some other jump instruction to sort of terminate it, but without a jump instruction, this essentially will run forever, and you get stuck in an infinite loop if you don't have anything in there. So it's typically not ideal to have a run forever loop, but that's how you would do it. I wanted to do one more thing. The next part about while loops, but there's one extra comparison I want to show between, I don't know if it's in my notes, so I might get this wrong. I might have to correct myself. But if I wanted to compare range for loops to these for statements, these regular for loops, this is what I would do. I would say for, let's say int x in v print x, right? This is kind of what happens if you were to go through a sequence, right? If you wanted to write the equivalent kind of thing in with a regular for loop, what you might write is something like this. For int star p equals v dot begin, I'm going to run out of space. P is not equal to v dot end plus p. And then print dereference p. Okay? So slightly different in terms of the type of variable we're using. Here we're using an x, here we're using a p. But essentially, what are we iterating through, right? The bare bones thing we're iterating through, we're starting with the first address, and we're incrementing, that's the plus p thing, we're incrementing p until we reach that last address, that address that just goes past the vector. And when that happens, this is now, this Boolean expression is now false, because while p is not that last address, we keep running. So when it does become that last address, this is now false, and we jump out, which is kind of like what we're doing here, right? So the initial condition is v starts at v dot begin. P starts at v dot begin, and while p is not quite reached that address, we run the loop and we increment p until we do reach that address, in which case we jump out. Okay, so that's the only thing. Ooh, okay. While statements. So we talked about for loops. Now we got while loops. 9.5.3 while statements. A while statement executes until its condition is false. So while statements are good when there is no obvious loop variable to introduce. So especially if you don't know how many times a loop might run, that's when I would say a while loop is, so many times. A while statement executes until the condition evaluates, condition evaluates to false. That's fine. So good for when there is no obvious loop variable to introduce. So yeah. While statement executes until the condition evaluates to false. Yeah. So what was I saying? So if you don't know exactly how many times a loop has to run, like how many times it has to repeat, then while statements are generally better. So if you catch yourself, especially if you catch yourself not having like if you find yourself wanting to do something like this, right? Like maybe you have a condition but you don't have any declaration. Generally speaking, it's probably better to just use the while loop, because the while loop basically takes away any need for like the declaration part. You just put in the condition, right? So that's what I would say in terms of when to use a while loop versus the for loop. So I guess a bit of a concrete example of this is a game loop. So if you're building like a game, very typical structure or very typical concept is the game loop, which is like, every so often you need to update the objects of your game, and that's just going to be running continuously. There's no real reason to there's no real way to predict how many times it's going to run, I guess, because depending on how long you play, that will run for however long. So in that sense, you might have some Boolean variable, game is running. I don't know why I capitalized that. That's really weird. Game is running. And then you say while the game is running, then do all your game stuff. And as part of your while loop, you might listen for if they click log out or click quit or something, which would then set game is running to false, and then that would make this condition false, and then it would jump out of the while loop and get down to here. So that might be something. But you can imagine like writing a for loop for this isn't necessarily, again, there's no real loop variable. I guess there is kind of. You could do something like for, I think this would work, for bool game is running, and then game is running. Keep running out of space. I guess the equivalent would be for bool game is running, and the condition would be bool, not bool. The condition would be just game is running, and then there'll be no update, and then do the same stuff. So yeah, something to bear in mind is there is always a mapping from a while loop to an equivalent for loop and vice versa. There's always some kind of way to convert them. But generally speaking, for loops, you generally expect to have all three parts. So in this case, you're missing the update. So if you're missing one of the parts, it's probably like more somehow obvious, I suppose, to use a while loop. But I guess it's programmer's choice when you use which one. Okay, so that's not much to say there. I think if I should have said more, but that's fine. Then we have do statements. So this is point 4, I think. Yeah. Do statements. I will preface by saying that the book literally says avoid do statements because they can be kind of weird. But I think there are occasionally times when they are helpful. So essentially, got away with it. Avoid do statements. There's an extra quote or whatever. Do statements are like a while loop or like a while statement, except conditions. The condition appears after the body. After the body, which means that the body always runs once before the condition is checked. I don't know if I have an example for this. Oh, I don't. Oh, I kind of do. Kind of wrote pseudocode, I guess. So, I scribbled it out. A bit worried, but essentially, I hope, yeah. I think the biggest use case that I've seen do while loops, like do statements, is like if you're taking a user input, because the expectation is you always expect the user to give you at least one character, just about, I think. So in that sense, you or at least you always expect to prompt the user to give at least one character. So in that sense, you can always you can expect to run that loop at least once. So you might as well use a do while loop. But I don't think there is much problem with avoiding do while loops and just using while loops the whole time. But you might do something like this: do, and then this. Print, please enter a character. And then you do something like standard input. You plug into some C, so you might have defined char C beforehand. And then you like print the character or something. Print C after they plug it in. While maybe C is not equal to Q or something, where Q means quit. So the idea is you're always expecting that this line, especially this prompt, please enter a character, and the first character to be plugged in, you always expect that to happen. So in that sense, you might use a do while. But that is an assumption you're making. You're making the assumption that this block, this body, is definitely for sure going to happen. Everything from printing the prompt to taking in a character to printing the character, all that's going to happen. Especially with user input, it can get a little. You're kind of hoping for the user to cooperate. If the user kind of does some weird stuff, then maybe it doesn't quite work out the way you think it does. So in that sense, just be a little bit careful with using do while. Make sure that it's your assumption of, oh yeah, definitely I'm going to run the loop at least once. Make sure that that's well founded before you use it. But literally, the book, I'm pretty sure this is a direct quote. I'll double check if I've misquoted, but basically it just says don't use them for the most part because there's no real need. Okay, 9.5.5. So loop exit. So this is about the jump conditions or the jump instructions that you can sort of use in, especially for loops. We saw break with switch statements to avoid the cascade effect. But we will see that they are particularly used in loops as well. So loop exiting, loop exit. So loops have conditions, right? We've seen that. The loop will terminate if the condition is evaluated to false, right? We've seen that, especially in that for loop example, right? When I was less than 10, it ran, and then when it got to 10, it terminated, and we jumped out of it. However, there are other methods for this jumping out. However, we can also force a termination using certain keywords. So the condition that you give itself might still be evaluating it true, but we can request for an early exit. So the keywords are, we've seen break, there's return, which is sort of specific for functions, go to, which we talk about at the very, very end, and throw. Throw is like very specific to error handling and stuff, which I think is its own chapter, so I don't think it's mentioned here. Return, I think, is a part of functions. Break is the one that we look at in particular. So break, looking at break, we break out of the innermost, in brackets, loop or switch statement. Why do I say innermost? or first I should say. So essentially it lets us exit a loop in the middle of the body. So for example, imagine I have while true. So I'm just letting this while loop run forever because true is always going to evaluate to true, right? No way is the condition going to evaluate to false. But I'm taking standard input, std.cin, plugging it into some character c. But if c is equal to the new line, which I write like this, right? \n means new line, like I hit the enter key. Then we can break. So that's to get to there, and that's to get to there. So what's happening? Well, this is going to run continuously, right? I plug in Q, I hit my character, A, B, C, G, T, 4, colon, whatever. All those characters are getting plugged into C. When I hit enter, what's going to happen? The new line character, which is associated with the enter key, is going to be put into C. Then we'll do this comparison check. Is C equal to the new line character? For all the other characters, the answer was no, it was not. So we skipped the if statement and we resumed the loop. But as soon as we hit that enter, this condition now is true, right? C does indeed equal the new line. So we hit the break. We hit the break statement, which means the innermost either loop or innermost switch, like switch scope, gets broken out of. In this case, the innermost loop is this guy, right? While true, down to here. So when we see that break, we break out of that innermost loop and we end up over here in terms of our execution. And whatever instructions are here, we run from there. So even though it's a while true loop, in which case technically it could run forever, we have a way of exiting early in using this break statement. Now, innermost, it's important to remember this innermost thing, because imagine if I have while true, and then for some reason I had another while true or something. I don't know why I would do this, but just to get my point across. How do I do this? While true brackets. Okay, this is a really stupid example, and then imagine I just have my break straight away. Okay, really think about what's going to happen in this situation. I enter a while true loop, which is meant to run forever because true is never going to become false. I enter a nested loop, a loop within a loop, so to speak, while true, and that's running over and over again. As soon as I enter this loop, I hit break, right? Now, while the intention might be to break out of both loops, you're only going to break out of the innermost one, right? The most nested one that the break is associated with. So in that sense, while true, I break out of this loop, but then I'm still within this loop, so I return back to here, and then we enter again, break out of here, get back to here, go and break, and we actually are stuck in an endless loop. If we had a second break, like here, then, this is a really stupid loop now, but we would enter here, break out of here, get to here, break out of here, and then get to here, right? You need to have a break that is sort of within the same scope as the loop that you're looking to break out of. If your break is in this scope, it will only break out of that innermost loop. If the break is then here, it will break out of the scope that it's in terms of loops, in terms of the scope of the loop scope. It will break out of that scope, and it'll get out here. So breaking will only break out of one scope at a time. Same with switch. We had all those breaks for the different cases, but every time we're breaking out of the overall switch scope. Okay, so there is another keyword, continue, which isn't exactly an exit, but it's kind of a skip. It skips an iteration. So yeah, notice that continue is not one of these keywords, it's like a different one. But continue, okay, good, avoided it. Continue is skip one iteration of a loop. After a continue, the update statement is run for a for loop specifically, right? Because then the for loop has the update statement for a for loop. So when I say for a for loop, I mean for this semicolon this this is the condition and this is the update statement. When continue is run, it hits the continue. It executes this, the update. We'll go through a concrete example in a sec. when a continue is hit, the update statement is run, and then the condition is checked as it normally is, right? Before we re-enter the loop body. So, super concrete example. Imagine we have something like void. Find all primes given an integer n. So the idea is we're going to go from 2 up to n inclusive, and we're going to check all the values that are primes. Okay. So what are we going to do? We're going to say for int I equals 2, I less than or equal to, because we want to check n as well, less than or equal to n, plus I, so that increment I. And this probably isn't the best way to write this, to be honest, but to use the continue, we could say if, imagine I have some magical function that can check if a number is prime. So if is prime I, right? So is prime is just some function I made up that we're pretending is able to do its job really well and check if a number is prime. So if is prime, and notice I have the negation, right? Because the exclamation mark at the front. So this is basically saying if it's not prime, if I is not prime, then continue. Otherwise, we can print I. I'm missing a. So what's going to happen? Let's say n equals 5. So the range I will take 2, 3, 4, 5, and I guess 6 technically as well. Okay. Let's think about what happens. For int I equals 2, we start at 2. If I is not prime, right? I is prime. 2 is prime. So this overall thing will evaluate to false. It will skip over and it will print 2. It will print I, which is 2. So it will print 2. Fantastic. Then it moves on to 3. It runs the update statement. Now it's 3. Try it again. If it's not prime, that's false. It is prime, so this is false. We jump over, we print 3. Now we get to 4, because we run the update statement. We're now at 4, we try again. If I is not prime, 4 is not prime, right? Is prime not? It's not prime. So this actually evaluates to true. We now hit our continue statement. What does the continue statement do? It skips an iteration of the loop. That is, we basically immediately sort of stop the loop body, run the update statement, and start again. So it's now we're at 4, right? N equals 4. It was 4. We run the update statement. It becomes 5, and we start again. We're still less than or equal to n, right? So that's fine. If I is not prime, but it is prime, so we jump over, we print this guy. And then we go to update, it's 6. That's now bigger than n, right? N is 5. 6 is now bigger than n, so condition is now false. We jump out. We end up over here, right? Hopefully that makes sense. Why are we printing 2, 3, 5? Because we skipped the iteration where I was 4 because we hit this condition and we continued, meaning we immediately ran our update statement and we checked our condition. It was fine, and we continued. We continued on. Okay, so that's the continue. Imagine if instead of this, just to really break through what this break statement does, really just to make sure it makes sense what this break statement does. Imagine I print I, so I got rid of the negation, right? So it's just is prime now. Oh, that's not really legible. That says is prime. Okay. Print I, and then break. Right? Is prime. Okay. So what would happen in this case? Well, I'm going to rename the function to be find first prime. This is kind of a stupid function now that I think about it, but it's fine. Again, if n equals 5, what's going to happen? We start at I equals 2. If it is prime, and it is prime, so that's true, we're going to go into here, we're going to print I, which is 2. We're going to print I, and then we're going to immediately break, which means we're going to break out of the innermost, either loop or switch. In this case, it's a loop, it's a for loop. So we break out of this guy, and we continue on our merry way. We continue on to like here, I guess, which I guess is the end, so then we terminate. This doesn't make any sense. Ignore that. We break out of the for loop. When we hit this break statement, we break out of this for loop, so we're no longer within this scope, so we're outside, and maybe the function returns or the function terminates, whatever. But yeah, the break just immediately jumps out of the innermost for loop, whereas the continue just runs the update statement again. For a while condition, basically, for a while loop, there is no update condition, so essentially, you just restart the loop without updating anything if you hit a continue in a while loop. Yeah, okay. So 9.6. Which is about Goto statements. Now, again, similar to do-while, Goto statements aren't really seen much in particularly high-level programming. You don't really expect to see it unless you're doing some low-level stuff. But in terms of syntax, you would expect it to look like Goto colon label for some label, and then in terms of how do you introduce a label, it would look like the label name colon and then some statements. So yeah, it says here generally it's not in high-level programming, but the scope of a label is the function it is in. So where is a label accessible? It is accessible within the function that it is located in. So what this means is you can jump into and out of blocks. But the restrictions are you cannot jump past initializer, right? Similar to like the switch case thing. If you try to jump past an initialization, it's going to cause problems. And you cannot jump into an exception handler. What is an exception handler? We will find out in chapter 13.5, which is actually a bit closer than I thought. I thought it was way far, but this is 13.5. But essentially, just bear in mind for now that, yeah, this idea of jumping around, you can't jump past an initializer, and you can't jump into an exception handler. So, again, I've given some like generic structure for what a goto looks like, and I've given some basic ideas. But what does it really look like? What? I think that's meant to say. Okay. If you were to look at the typical use, I guess I have to. Chunky example to write up. The typical use is breaking out of a nested loop or switch statement. But I don't think I've ever used a nested switch statement. But nested loop. Because remember, breaking only gets you out of the innermost loop. Breaking gets you out of the innermost loop. So if you want to break out of all the loops all at once, you can use a jump or a goto statement to basically just skip over all of the things, all of the loop. All right. So imagine you have. So for my example, we have our main function. I might have to write a little bit small. Int main is what that says. Imagine we start with a 2D array. Very typical use case for nested loops is 2D arrays. And I will use color here. So 3, 2 for M, right? We've got 3 children, so 3 arrays. Each of which contain 2 elements, integer elements. So 1, 2, 3, 4, 5, 6. Okay, so we've got 2D array, which has 3 child arrays in it, each of which have 2 elements in it, right? Hence 3 and 2. Imagine we start a for loop, and the idea is I want to basically read each of these values. So for int I starts at 0, I less than 3, plus I. And then we have our nested loop for int j equals 0, j less than 2, plus j. Maybe we can start by printing. Notice that I can print mi at j, and I'm very confident that this is going to access a legitimate value, a legitimate address. It's going to do legitimate indexing on m. You start there. But then, let's say I'm looking for the first number that is divisible by 3. So if m at I, j, mod 3 is equal to 0, that is the remainder, right? When you divide by 3 is equal to 0, so divisible by 3. Then go to found. This is my approach to do it in color. Go to found. Okay? And then just a bunch of closing brackets. So close that guy, close that guy, close that guy, and close this one. Okay. No, we're not done. I need to put my found label. So we do found, colon, and then we can print something like m, the array m, has a value. I can't even say that, can I? We can just print exited the loop now. Because I can't even be sure that I hit this label for any particular reason. Okay, hang on. So, let me close this. Okay, let's talk about this. First of all, remember that if we put m of 0, like for I, if we put m of 0, that means we're talking about the first child array. If we put m of 1, we're talking about this child array. And we talk about m of 2, we're talking about the final child array, right? That's why, in terms of my I values, I starts at 0, and I always stays less than 3, because I want the values 0, 1, and 2, all of which are less than 3. Similarly, let's say I is 0. If j, right, m of ij, if j is 0, then I'm going to be looking at the first element of my child array, right, the 0th index, the first element. If j is 1, then I'm looking at the second, or the index 1 element of my child array. That's why I say j equals 0, j is less than 2, right, because j is always going to be 0, then 1, then 0, and 1, then 0, and 1. So in terms of, I guess, first things first, just because I guess there's no specific thing that talks about nested for loops, so we might have to quickly talk about it here. What kind of pairs of I and j are we going to get? We're going to start with, I guess if I was a table, I and then j. We're going to start with I equals 0, then j equals 0, right? I equals 0, j equals 0. This inner loop's going to happen, and then j is going to increment, and then j is going to be 1, and that's going to increment. So that's going to be the next pair. 0, 0, I equals 0, and then within that I equals 0 loop, we have j equals 0 and j equals 1. Then j is going to be equal to 2, which will terminate the inner loop, bring it back to the outer loop, and I is going to increase by 1. J is going to be, we're going to come back into the inner loop, j is going to be 0, then j is going to be 1, while I maintains its value of 1, then j is going to become 2, and we jump out. And we terminate out of the inner loop and go back into the outer loop. I increases by 1 again, it becomes 2, which is still less than 3, so we go back into the inner loop. J becomes 0, then j becomes 1, and then j becomes 2, and we iterate out. So j becomes 2, we break out, we terminate out, come back into here. I becomes 3, because I was 2, it increases by 1, I becomes 3. That causes this to be false, we jump out of the whole thing. So that's, in theory, what's going to happen. Right? And these are the pairs in order that I and j are going to take. So let's see what actually happens with this goto. So for int I equals 0, go into the inner loop. For int j equals 0, so we start here. We print m of 0, 0. So m of 0 looks at the first child array, and then the next 0, the j equals 0, means we look at the very first element. So m0 of 0. We look here. Print it, it prints 1. Is it divisible by 3? No. So we don't do the goto found, we actually just come back to here. Then j increases by 1, so we've done this one. J increases by 1. Now we're looking at 0, 1, so we're looking at this element over here, right? 0, then 1. So it's 2. Is that divisible by 3? No, so we don't bother with the goto, we jump over it, and we loop again. Then we actually terminate out of the inner loop. I increases by 1, I becomes 1, and now we're back into the inner loop where j is 0. So we're looking at I equals 1, so this child array, and j equals 0, which is this guy here, so it's 3. We print the 3, and then we say, is it divisible by 3? Well, yeah, it is. So we go to found. So we have printed 3, and then we jump out, and we say print, and then we print exited the loop now. Okay? What does that mean? That means we're no longer in our nested loop. So after we got to here, in fact, all these guys over here actually didn't even happen, because we jumped out of the loop completely. All right? Think about what would happen if we used a break instead. Think about what the difference would be. In fact, what would happen is we would break out of the inner loop, meaning the I would increase by 1. Right? We would break out of the inner loop, go back to here. I would increase by 1, so it would become 2, and we basically would only skip the 1, 1 row. 2, 0, and 2, 1 would actually run as normal. But that's why. So in this case, we've chosen to do go to found. because we want to jump out all the loops. Now, I can't actually print here saying, oh, we have definitely found an element divisible by 3. I can't print that because it's not that found won't run if we don't jump to it, right? Let's say we iterate through this entire thing, and we have values that aren't divisible by 3. Right, so 1, 2, 7, 4, 5, 8. So all the same looping will happen. It will print 1, 2, and it will print 7, 4, and it will print 5, 8. It will never run the go-to because they're divisible by 3 is not going to happen. But after we terminate out of the outer loop when we're here, this will run as if the found label wasn't there. This will print no problem. So printing something like, it's divisible by 3 isn't actually valid. Like we found something divisible by 3 is not a valid thing to print because this will run regardless, right? And that's, I think, one of the big reasons why I don't think I like go-to statements and labels. Like, it's very easy to think that only if I jump to it will it run, but that's not the case. It will run regardless. It's just that you can sort of use it to jump out early if you want, but just don't forget what conditions have been met, I guess, in order to get here. Either you jumped out early or you just naturally fell into it. Either way. And it says here, jumping into new scopes or new loops can be confusing. So imagine this found was actually within a different for loop, right? Like it's possible, but it can be difficult to follow. And in that sense, it's probably not a good idea. Which is why, in general, I think go-to statements are a bit dodgy, and it's generally avoided in higher-level programming. But that's how go-to works. It's just a big leap or big jump outside of things, and typically used for jumping out of multiple scopes at once. All right, and the last bit, nice and chill, is 9.7, which is on comments and indentation. Good. All right, so in terms of indentation, there's no particular reason to prefer one style of indentation over another. So, if you're the debate of spaces versus tabs, the size of the indentation, the book doesn't give any particular indication of which one is correct. Again, always remember consistency is key. So if you're brought into a new project and someone has been coding a certain way with a certain style, you generally want to follow it. But otherwise, there's no real reason why the book would prefer one over the other. The only kind of general statement, the only real sort of rule that is typically followed is statements within a block are more indented than statements outside a block. Typically, this is just a way of showing what's in a more inner, what's in a more inner scope and what's in a more outer scope. So, you might have a function, and that introduces the function scope, and then so lines underneath it or within it should be indented. And if you have a for loop, that introduces the statement scope, so things should be indented even more. Right? So this idea of indentation usually just to indicate changes in scope, narrowing of scope. Yeah, so that's pretty much that. And then for comments, in terms of syntax, one-line comments, you typically write like this, right? And then blah, 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 blah. And comments, I should probably say comments are basically things that the compiler won't acknowledge or won't recognize, won't be part of the program at all. It's usually just ways for programmers to remind themselves or explain to other programmers what code is doing and stuff like that. Now, so this is for one line comments, and the other way is if you have like / and then a star. So this is 2 forward slashes, / and an asterisk, and you have multi-line comments and star asterisk, right? So this is multi-line. So now comments it's very easy for comments to get a bit out of hand. You can fall for the trap of feeling that you need to comment absolutely everything and explain absolutely everything. A lot of the times, your line of code is quite self-explanatory, right? Int I equals 3, you don't have to say that the integer I gets the value of 3. There's no point in commenting that because your code, in a sense, is self-explanatory. So you want your comments to be up to date, meaningful, descriptive. Don't explain what is happening, especially line by line. Don't explain what's happening line by line. Rather, explain the intention of code, especially larger blocks of code, intention of code. I'm talking, you want to have a multi-line comment on the overall function, intention of an entire function, a large function. Even small functions probably don't need comments, but if you have a particularly large function, then that would merit a comment. And at the top of a file, you might have, this program was written by a person at this date, and in that sense, you would want to make sure that that's up to date. And yeah, so meaningful and descriptive is more so like if you have something that's a bit more complex, like an overall function that's a bit more complex, then maybe a comment is useful to really explain what the purpose is, not necessarily what's happening line by line, but what the overarching idea is. And if you do feel like you have to explain things line by line, then maybe the way the code has been written could be improved. There is like an extra detail regarding nesting with multi-line comments. If you have something like this, and then within the multi-line comment you have this, how this is interpreted is this is the multi-line comment, right? And this is just like randomly. So this, I believe, will cause an error because we'll say, why have you put that there? It won't recognize that this is the comment and you just added nested comments inside or something. So avoid nested comments, I guess, is the overall takeaway there. But that is the overall chapter 9. And so that's that's a pretty rigorous introduction. Oh, let's just say 9 point. Wait, what? Oh, I was meant to erase this like ages ago. Oops. Anyway,